Alright, crikey, good day and welcome. Today we're looking for 4 enzymatic scenarios in action. Those, of course, are your normal binding, competitive inhibition, non-competitive inhibition, and your influences that play on cofactors. Let's go find them. Crikey, hello there. For some of you who don't know the purpose of enzymes, this will give you a little idea. Enzymes act as catalysts that speed up metabolic reactions by lowering the energy barrier. Here's the diagram of the energy activation. Here we have an exergonic reaction with your reactants or substrates on the left, the transition state as this hill in the middle, and the products on the right. The energy difference between the transition state and the reactant is called the activation energy. Here is the reaction without the catalyst. Now let's add the enzyme, aka your catalyst. We can see the activation energy, or the energy necessary to break the bonds of the substrate, is much lower. We can also see that the energy released by the reaction, known as delta G, is not changed by the enzyme. Without the enzyme, the substrate requires much more energy to reach its transition state, and this would take much longer than with the help of an enzyme. Crikey! Since enzymatic reactions can be found in all animals, let's take a look inside this giraffe and see what we can find. Aye, crikey, look what we've stumbled upon here. It appears to be an enzyme that is about to facilitate a reaction using normal binding. The structure of the enzyme is composed of many proteins. Here, the substrates move closer to the enzyme and fit perfectly into what is called the active site. Only these substrates fit in this active site, much like a key fitting into a lock. Notice how the enzyme changes its conformation slightly as the substrates enter the active site. This is called an induced fit, which allows for the substrates to be aligned perfectly. Crikey, look at it go! After the substrates undergo a reaction, the resulting compound is called the product. What a beauty! The brilliant part is the enzyme is not used up in the reaction. In fact, it can go on to react many more times with the same type of substrates. Here we saw an enzyme binding 2 substrates, but they can also facilitate many other reactions, such as breaking substrates down or changing substrate conformation. Let's observe some more enzyme activity. Look what we have here. We're about to witness competitive inhibition. This really is exciting, mates. Notice how a compound attaches directly to the active site, blocking it from use. The active site is no longer available to the substrate. Now, when substrates approach the active site, nothing happens. It's like putting gum into a lock. Thrilling, isn't it, mates? Gee willikers, if you think that was neat, wait until you see this. There's actually another way that enzyme activity can be inhibited called non-competitive inhibition. This inhibitor binds to a part of the enzyme other than the active site. Once bound, the substrates are unable to bind with the enzymes because the inhibitor changes the enzyme's conformation. Now the lock of our lock and key mechanism is the wrong shape for the key. Crikey, that's not good. Well, what do we have here? This enzyme needs the assistance of something else in order to be useful. How about a cofactor? A cofactor is a non-protein compound that assists the enzyme in binding to the substrate. Watch as it provides the perfect conformation for a catabolic reaction to occur. Crikey, that's a beauty! Well, I hope all you mates enjoyed this episode of Enzyme Structure and Function. Tune in next week where we'll be diving with stingrays. Hopefully that goes well.